Now, let's talk about L5. Okay, why am I specifically picking on L5 here? Didn't really spend much time on L1 or L2 or anything else. Well, L5 and 3D model assistance go together like rock and roll, bread and butter, bed and breakfast. I'll show you why. The key feature of all L5 signals is that they have a 10 times higher chipping rate than the corresponding L1 signals for that constellation. And so the correlation peak that I mentioned right in the beginning is 10 times narrower than it would be for the L1 signal. And that is the single most important thing about L5. In itself, that's a good thing. Without anything else. In the open sky, that's a good thing because you get more accurate measurement from L5. But that's not nearly as powerful as the magic that happens when you combine L5 with 3D model assistance. Because when you get in an urban canyon and you get reflections, if the signal is blocked, so if you imagine this green signal is blocked and you're just picking up the blue from a reflection, what we see is that when you get one reflection, you get many. And you've seen this in every picture I've showed you of the actual rays. You've seen that there are many different paths in a big city. There are many paths from a single satellite to a user. So you almost never get a single reflection. You get multiple reflections. And with L1 in GPS, for example, the peak width is plus or minus 300 meters. These multiple reflections all overlap. And what many of you will be used to seeing is this kind of multi-path picture, and you see this, you see, oh, I get it. There's a correlation peak, there's another correlation peak, another correlation peak. The actual output of the receiver is some blob like this gray. That's bad enough, because by the way, keep in mind, the distance from this little sub-peak to this peak is about 100 meters, so that's a big error. This is bad enough, but this static picture is not nearly as bad as the reality. And unfortunately, in papers, we can't print GIFs, but on a screen, I can show you a GIF. The thing to realize here is that these different signals have different phases and slightly different Dopplers from each other. Even if you're stationary, they have different Dopplers because the satellite is moving. And so this GIF shows you a representation, a real-time representation of the constructive and destructive interference between these overlapping non-line of sights from a single satellite. And so what you can see is that it's actually impossible to predict at a specific time what the receiver should be measuring. Because at this moment, it'll be measuring the signal here, and a few seconds later, it's going to be measuring something 200 meters away. And so it's only possible to model L1 in a statistical sense where the variance on the statistics is 50 meters or more. Whereas with L5, we frequently have, most commonly, we have distinct peaks, at least distinguishable peaks. Even if they overlap a little bit, top of the peaks are distinguishable, and therefore you can predict the delay with great certainty. So that is the magic of L5. So in summary, L5 alone is not going to solve the non-line of sight problem because there's still a bias with an L5 measurement. It's just more precise. But it's this precision that gives us the magic because we can use it to model the reflection, even multiple reflections. And so 3D model assistance plus L5 provides the solution that we really want for non-line of sight signals. Okay, and so finally, and if you made it this far, congratulations. And I'm briefly going to talk about actual deployments that have been done in phones and the results that we get.